today we have the pleasure of having Julia Sordyl from Uppsala University, who would tell us about how to turn rocks to functional materials with a specific focus on REs. This lecture, it's being recorded and it will be shared via the studium to those of you who could not be here today with us in the live session. So Julia, the stage is yours.
Thank you very much. Thanks for introducing me and thank you for inviting me to give that lecture. So, I am a postdoc at the Department of Earth Sciences at Uppsala University, and my background is in geology. So, I would like to start my presentation with this life cycle of Earth elements because basically it also shows the agenda of my presentation. I'm gonna talk step by step, starting a bit with exploration and mining, then focus a bit more on beneficiation and metallurgy of Earth elements, and then we'll try to answer the question, why do we really need that? Why is so much focus put on Earth elements? Are they really so unique? What we can use them for? And then we'll touch upon a recovery, or more like a target for recycling. So to make this process more sustainable and more circular. I'm not going to spend much time on geopolitics and stuff like that, but I thought it's worth mentioning the proportion of China's rare industry in each of these stages. So, in terms of exploration and mining, 60% of this industry belongs to China, while 40% to other countries. And in the next slides, I'm going to present what countries. And then in terms of metallurgy and material preparation, almost 90% belongs to China and just small percentage belonging to the other countries. And situation change again with thermal applications. About 66% depend on which year belongs to China, and the other percentage belonging to the other countries. And that's it. Let's start with exploration and mining. So the very beginning of the whole life cycle. Exploration is basically defining RE ores and defining RE mineralogy. And there's a lot of exploration projects ongoing all around the world, at every continent, at so many countries. But the biggest RE reserves are held by China, and then Vietnam, Brazil, Russia, India, Australia, and smaller percentage belonging to United States, Greenland, Tanzania, Canada, South Africa, Thailand, and other countries. In terms of mining, it's actually three main mines that are exploiting REs currently, and those are Bayan Obo in China, Mountain Pass in the US, and Mount Weld in Australia. And there's a few smaller mines that are operating. And if we take a look on this graph, the inner circle represent the active mines, and the outer circle represent big RE exploration projects. And the thing is that REs deposits are quite complicated, and they represent different types of deposit. Most of them are carbonatite type, but it doesn't mean that all of them are the same. There are also alkaline, hydrothermal, ionic clay, placer, and other deposits. And what is complicated is that each type of this deposit bring different mineralogy. And mineralogy of this deposit is usually quite complex. And usually it's not just a single RE mineral in the deposit, but usually there's several of minerals. And the thing is that all these minerals have different chemistry. So there are over 250 known RE minerals, and they are silicates, phosphates, fluorocarbonates, or oxides. But the main REE ore minerals are this four. It's bastnäsite. 70% of REEs that are currently mined come from bastnäsite, which is light earth element fluorocarbonate, and then monazite, which is light earth element phosphate that also contain thorium, that brings some environmental concern. And then xenotime, which is heavy earth element phosphate, and then ion adsorbed clays that are the main source of heavy earth elements. So when we go to beneficiation and metallurgy, sometimes we can see graphs like this that simply say that, yeah, we just take out the rock, we beneficiate, meaning we just concentrate the minerals of interest via some method, and then we do some metallurgical process, which is specific for a specific concentrate, and here we are, we have a RE product, right? Or it's even easier with ion adsorbed clays because they do not need a beneficiation. They can just go directly to a metallurgy and it's in situ leaching, and there it is. There is an RE product. So it looks easy, and I understand that it is just a schematic diagram, but in fact it is way more complicated and brings a lot of challenges that I'm gonna shed some light on right now. So it starts with a beneficiation. As I said, it's basically concentrating of a mineral in question by crushing and grinding the rock to reduce the size and then concentrating via various methods to get a concentrate, so to make the further processing cheaper and more efficient. And in here, I show three different beneficiation methods. And already this stage, as we can see, is quite complex. It's usually not just one step. There's several steps, and it's just to get a RE concentrate. The thing is that a beneficiation method always needs to be adjusted to a specific deposit and to a specific minerals. And those are examples of some beneficiation efficiency. So for bastnäsite, which just a reminder, it's a carbonate mineral. It's a main RE mineral that is in the industry for many years, but still the efficiency is not perfect. So the range is quite broad, from 45 to 95%. It, of course, depends on the scale. Laboratory or pilot tests usually yield higher efficiency, around 80 to 95%, and industrial scale is usually a bit lower. But it's okay because bastnäsite is rich in rare oxide, so usually a grade of a concentrate can be up to 70% of rare oxide. Similar thing is with monazite, that is a phosphate, different method of beneficiation, and also different recovery to concentrate. Again, the same story. Lab test and pilot test usually yield higher recovery, industrial scale usually a bit lower, but still okay because the concentrate is a high grade. And then xenotime, same here, 70 to 90%, so it doesn't reach 100% of recovery rate, and relatively big percentage of earth oxide in the concentrate. Xenotime, so it's mainly heavy earth elements in the concentrate. And then for eudialyte and apatite, those are the minerals that are not currently mined for REs, but there are several projects that are focusing on these minerals. So there's also several reports and papers on beneficiation efficiency of these minerals. This is only lab or maybe pilot scale. So the efficiency is quite good For udilite, 70 to 85%. For apatite, slightly higher because apatite is not a new thing. It is a main source of phosphorus. So apatite was beneficiated for many years now. Therefore, the recovery is quite good. But these minerals have a much, much lower percentage of rare earth elements. So the concentrate is about 1-2% of rare earth oxide. And the thing is that for the main minerals, the beneficiation techniques are rather known and they're tested and described. However, there is still room for improvement. As we can see, there is definitely a room for improvement in terms of efficiency, but of course also in terms of energy and water consumption, and also in terms of use or of greener chemicals for that process. And now it's going to be even more complicated if we go to metallurgy. So there is an industrial flow sheet for processing of bastnasite, and the main process is focused on oxidation roasting and then HCl leaching and caustic conversion. It has its own benefits, like it's a low cost and RE recovery is high, but it brings a lot of challenges. The procedure is quite complex, as we can even see it from this graph. There is a large consumption of chemicals, and there is an environmental pollution of fluorine-bearing waste gas and water. Therefore, some alternative flow sheets were invented that are a bit simpler. We can see the flow sheet is shorter. The biggest benefit is that fluorine can be recovered, so there is no environmental pollution of fluorine. However, it has its own challenges. Of course, it yields lower RE recovery, so there is always a price. If we take a look on monazite, which is a phosphate, the main process for monazite is hot acid digestion, followed by filtration precipitation. Process is simple. It yields high RE recovery. However, there is a severe equipment corrosion. There is a generation of radioactive waste because thorium is present in monazite. There is a generation of roasting fumes. And in terms of economics, phosphorus is not recovered, which is a big challenge. Therefore, there is another flow sheet that have another approach using a caustic soda decomposition. And it's excellent because it can recover phosphorus, it can recover thorium, which yield economic benefits. It doesn't really produce harmful gases during the treatment. But this procedure have limitations, like it's mainly for a high grade concentrate, and also it requires high pressure. It generates a significant amount of wastewaters and it consumes excess alkali. So again, there are benefits, but there are a lot of challenges in processing of these minerals. And then we have mixed concentrate. So it's bastnasite and monazite together. So the flow sheet include kind of like a combination of previous methodologies. And it's good, it's simple, it's low cost, and RE recovery is high. There is no concern about thorium because it is also recovered. However, there is a lot of impurity introduction, there is air water pollution, and there is still a risk of radiation. Of course, alternative flow sheets have been developed, and they can be easier and use a relatively clean process. However, they consume a large amount of wastewater and they are expensive. So even though those minerals are in industry for many years, they're still facing a lot of challenges in processing, and there is definitely still room for improvements for them. And when we take a look on those tables that I presented earlier, As I said, mineralogy of this deposit is quite complex. I only presented a metallurgical approach for two minerals, bastnasite and monazite. But what about all the others? There's a lot of improvements that need to happen because all these minerals have different chemistry, meaning they all need different treatment. And there is a lot of effort, for example, for recovery of REs from apatite, as I said, in lab and pilot scale. And in this table, I just put some examples uh, of taken from literature, and the approach is basically the same. It's again to leach RE cations into the solution and then separate them to get a refined RE oxides to be able to produce further products. So usually approaches are focused on using organic or inorganic acids to leach REs and then to precipitate them. And the tests yield quite satisfactory rate of RE recovery, but it's lab and pilot scale. Hopefully, it will be similar when it is tested in a bigger scale. So, to conclude this part of presentation, in the context of beneficiation and metallurgy of REs, it is really important to reduce environmental pollution, to lower production costs, and to increase production efficiency. And new ideas and technologies must be sought to accelerate progress in Europe and in other continents as well. And generally, these novel technologies should focus on utilization of cleaner, environmentally friendly reagents, on faster routes of production to lower the cost of production, and yes, to have a higher, to increase the efficiency. And it's important to remember that these future technologies should adapt to the principles of sustainability and low carbon emission in order to maintain competitiveness and industrial prospects. For that, I think it's important to promote international collaborations and collaborations between industry and academia, because it is not something that a single researcher or single company or even a single group can do. Like a joint effort is needed here in order to really accelerate the progress. And that part of my presentation was more maybe pessimistic, and I used a word challenge a lot. So now I'm gonna switch to more maybe optimistic part of this life cycle, which is usage of REs, and why is this so important? Why do we really care about them? So we very often hear that rare earth is a group of 17 elements. Yes, they are a group, they are very similar, but they are also very unique. And they have unique magnetic, luminescent, electrical, and catalytic properties because of their fundamental characteristics that make them so useful. So for example, some of them, it concerns neodymium, samarium, and dysprosium. They have magnetic properties, and it is due to a partially filled 4f electron orbitals. And magnetic fields are generated by unpaired electrons, and therefore RE materials can store a large amount of magnetic energy. And when they are combined with transition metals, they make the strongest types of permanent magnets that are available commercially currently. And those are neodymium iron boron magnets and samarium cobalt magnets. And then luminescent properties. It is due to the 4f4f and 5d4f electronic transitions, and it concerns yttrium, neodymium, europium, and erbium, and they emit light of a very specific wavelength. Therefore, they can be used as phosphors in energy-efficient light sources. For example, europium-doped phosphors proved crucial in the development of colorful television in 1960s, or erbium-doped fiber amplifiers intensify signal in high-capacity fiber optic lines. Yttrium aluminum garnet doped with erbium produce a wavelength of focused light that is particularly useful in oral surgery and in dentistry. So, next time, even when you go to the dentist, you can think of rare earth elements. And then electrical properties. This is due to the specific electron configuration and particularly a very specific behavior of 4f electrons. And this property concerns lanthanum, cerium, praseodymium, and neodymium. And as more 4f electrons are added from lanthanum through cerium, praseodymium till neodymium, it slightly changes 4f 5d interactions and it affects electrical resistivity. And therefore, they are useful for nickel metal hydride batteries, especially for the anodes of these batteries. The anodes of these batteries are made of misch metal, which is a mixture of these four elements, which brings benefits because a mixture of elements is cheaper when they don't have to be separated, and also it gives a battery a higher energy density, and therefore they can be used, for example, in hybrid cars. Catalytic properties, it concerns lanthanum and cerium, and there are different reasons for that. So for cerium, its redox flexibility, so it can basically the ability to switch the oxidation state, which make cerium useful in the catalytic converters on gasoline powdered cars. And what it does is cerium helps to convert poisonous CO into CO2. And then for lanthanum, it's the other reason. It is an acid-base behavior that make it useful in fluid catalytic cracking. So those were just examples, and ARI are applied in many other applications and usually in varied proportions. So not all of them are equally important, but each of them is unique and have its own unique characteristics that make them useful. And of course, the biggest market for arrays is still magnets. But if we take a look on a total application of arrays and compare only 2019 and 2025, so it's just 6 years, and we can see that the application increased significantly, and the prognoses are that it's only going to be increasing. The very last stage of REs is retirement of the products and hopefully recovery of them. So currently the targets for recycling, there are three main targets. The first one is the waste RE products, which is kind of obvious. And then mine tailings, and then, as always, others. In this case, the others are industrial byproducts, metallurgical residue, or wastewater. So, in terms of waste RE products, e-waste are the fastest growing type of end products, and they actually account for about 5% of urban waste. However, currently there is less than 1% that is recovered and utilized, which is very bad, and it leaves a huge room for improvement in that area. So recovery of arrays from e-waste require firstly some pre-treatment, which include disassembly of the parts, crushing, grinding, physical separation like vibration screening, density separation, conductivity-based separation, magnetic separation, and others. And basically then, since chemical properties of REs remain unchanged in the initial ore, tailings, or in the e-waste, they can circulate back to the metallurgical process. So hydrometallurgy can be used. There are some attempts of pyrometallurgy, biometallurgy, or electrochemical metallurgy. It's all to finally get a metal recovered and hopefully introduced to the market again. Another target that is mine tailings. So not necessarily RE mine tailings. So then that can be some old, for example, iron mines, because at the time when the mine was in production, there was an underdeveloped technology for extracting REs. And therefore the and also the economics at that time were not good for RE recovery, therefore they're just left in the tailings. But of course, again, it brings challenges as everything with REs. So first of all, RE grade in the tailings usually is low. Tailings also contain a large amount of other minerals, of gangue minerals, and also the proportion of really fine particles below 150 micrometers is huge, meaning that there are difficulties in beneficiation. And there is also a lack of effective hydrometallurgical methods for other minerals than monazite and bastnasite. So the biggest struggle actually is here in beneficiation of those tailings with that specific fine fracture. If that can be solved, they can follow the same road as the, let's say, original REs from mine. But there's a lot of benefits of REs recovery. Looking from a big perspective, it contributes to a sustainable development of the RE industry that is crucial. It helps to reduce the burden on limited RE resources. It also mitigates supply-demand conflicts. And then looking at the smaller, maybe more like local perspective, it reduces the natural disasters and environmental pollution caused by mining and by metallurgical processes. That is a huge concern. And those are, for example, landslides, air and water contamination. And also, just a very simple reason, but it could prevent the occupation of land resources by waste products and tailings because of their accumulation. And uh, considering that the overall recycling rate of REs is below 1%, the RE recycling industry still faces significant challenges, and therefore the recycling of secondary resources is actually full of development prospects. So those are the references and that I used the graphs in my presentation. And with that, I would like to thank you very much for your attention. I think I made it a bit faster than I expected, but it's usually like that when I just talk to the computer instead of interacting with the audience. So I
Well,
hope it's fine, but we have time for discussion.
thank you, Julia. Perfect. So don't worry about it. So it's good pace, good. So we have the floor for questions and comments, contributions, and I don't know if you can use the chat box or you can maybe
Mhm.
raise your hand as you wish. So Julia, maybe I can start with one question myself. People who would want to go for RE projects, like me. I decide now to be a developer of RE project. What are the sort of the thing that I need to pay attention? Where should I invest my money? Where is the hot
Yeah.
hot spot
Uh,
for going for REs?
Oh yeah, definitely. Sorry, I didn't want to stop sharing. I'll share
Yes.
again. Okay. So, well, basically anywhere. As I
Yes.
said, there are challenges everywhere. So, starting from, of course, exploration, mining, those are big projects, but then beneficiation of minerals. If we take a look on this table, we know how to beneficiate bastnäsite, monazite, xenotime. Now we know a bit more about apatite and eudialyte, but there's 250 other minerals. They all have different chemistry, different physical properties, so they will all behave differently in beneficiation. So there is a huge room for research projects and for laboratory tests here, definitely. Metallurgy, that's a huge room for improvements because anything new that will be developed, I believe that the more attention we put into that, it will finally uh, make it possible to have better and better and better processes. So there's uh, a lot of studies here and still a lot of room for any new researchers that would like to come with their unique ideas. And then going to the market, yeah, we know how to apply rare earth elements and how they can be used, but who knows, maybe there is definitely a room for fundamental research here. So who knows what other properties will be discovered that will make arrays useful. Who would think many years ago about using arrays for hybrid cars, for example? Now it's obvious and we use it. Who knows what will happen in next year? So definitely there is also room for improvement. And of course, recycling. That's always a really hard part. And as I said, there's 1% of arrays that are recycled. What about the others? So basically everywhere. If one have any ideas uh, and would like to contribute, I would say there is room for everyone
Mm, mm.
in here.
But I was more thinking about like, you mentioned I'm assuming much of the Chinese REs are from the clay rich REs, and whereas maybe others are looking at bastnäsite
Mhm.
and I don't know, maybe yeah, it
Well, that's
was
right, same time, yeah.
yeah. So would you make a quicker investment, cash flow if you go for clay rich REs, or as an investor rather than where we have established
Uh-huh.
technology? So
Well, yeah, oh, that's depend how you look at that, because of course, if you go for bastnäsite or clays and you already have the technology in place, that's easy. But
mm,
those technologies are actually very problematic and brings a lot of challenges. So it's also not that it can, yeah, it's very problematic. So maybe it's easier or better to go for something completely new and to
mm,
find a new technology.
mm.
I don't know. It's really hard. It's really broad, and uh, luckily, I am not an investor and don't have money to
No.
think about that.
No. All right.
Just,
We have a comments from one of the participants.
yeah.
Saying that you made a point on international cooperation, developing beneficiation processes for certain minerals or elements. We are witnessing the law passed by government for lithium producer that prohibits international collaboration and knowledge sharing in the field of lithium processing. On the other hand, I understand that such a decision uh, but yeah, I don't know. So, well, I think maybe the
Mm,
key point here is that while international collaboration, it may be good, but if we're going to have a geopolitics on critical raw
mm.
material, maybe you want to keep the technology, no? Or you maybe don't want to go too far.
Exactly. Well,
Yeah.
and it's also the question like it's different when we talk from university
Mm,
perspective because when we do the research, we don't really care about the geopolitics and stuff
no,
like that.
no,
So we just want to collaborate with the best researchers in our field. So
true.
in that sense, the collaboration is needed that there are so many research groups that do very similar stuff at the university level. If we could establish, I know it's basically impossible, but if the better collaboration could be established in that area, it would be good. And this is what I mean by international. So at the university level, when we don't care about
Yes,
all the
politics. Yeah.
geopolitics and about the borders, basically. But of course, it's different when we reach industry, and yeah, it changes the situation. So yeah.
Where do you see the prospect in the Nordic countries for REE, maybe a production? Would that be on I don't know, carbonatites, iron oxides, or we certainly don't have the clay reach, right?
No,
Or
we don't
no,
have it. Now,
yeah.
now there is a prospect, of course. LKB should be mentioned with a
Mm,
Pergeyer deposit that is investigated for RE recovery from apatite. And then yeah, Norasher with
yeah,
Udialite. So
that's true.
those are two not, let's say, not conventional minerals. But there are also other places, like we have a big mine tailings resulting from old iron
Mm,
mining that tailings contain apatite, but also can contain monazite, xenotime, and other minerals. So maybe we can contribute to recycling of REs actually. And yeah, well, Sweden is important in terms of REs because many of them were actually discovered here.
mm,
So yeah, there are places around. Uh, and yeah, I'm only talking about Sweden, but of course, Norway, Finland, they also have their own deposits. Yeah, the biggest thing is the economics behind that because deposits are there. It's important to say that there's a lot of RE deposits, also a lot around Sweden. The thing is, are they economic to be
mm,
exploited? That's
mm,
the question, according to the current technology that we have.
mm. Very good point. I don't know, there are no questions or any. Let me stop the recording first. So let me just thank you first, Julia, for a very wonderful, clear lecture.